Hey guys, my name's Cody, that's Jack. We're also partnered with Claire and Adeline, and we are working on the hot isostatic pressing sink defect modeling and mitigation project sponsored by Brian Griffin, who works for Howmet Aerospace. Our project is to develop a predictive model to predict hip sinks in castings that Howmet produces. HIP is a process that exposes parts to high temperatures and pressures in an attempt to close internal porosity. And when that porosity is near the surface, there's not enough material to actually press in and form an even surface, creating the surface defect, which we call a hip sink, as seen up here. Now, Howmet's process is pretty time intensive and expensive, especially when parts cost hundreds of thousands of dollars. So in developing a model that can help predict these sinks will help save the company both time, energy, and money.
Now, if hip sinks are driven by high temperature deformation, then a finite element analysis software like ANSYS Mechanical can accurately predict them. And the whole goal here is to produce a casting here on campus, send it to Howmet for CT, where we can get a CAD model, which we can then put into our software to model a hip sink. And then we also do the process here on campus to get a physical casting for comparison. Now, this is because at these temperatures, deformation is driven by climb dislocation motion. Now, our casting process used a permanent mold that was here on campus, which we then turned into a 3D CAD model. And this CAD model was then put into a casting simulation software called InspireCast. And what this allows us to do, it allows us to predict porosity in our parts. Where are we likely to get porosity? Now, this next plot is a plot of solid fraction, which shows in these filter block regions where we're getting our porosity that is causing these hip sinks, we are less than full solid fraction, meaning we're likely to have pores here in these areas. And we actually saw pores in these two castings. So these are CT of two different castings we sent to Howmet. The left one we saw hip sink, the right one we did not. And looking at this left one a little more closely, you can see pre-hip, we did not have, or it was a flat surface. And post-hip, we have a hip sink here that we can use as a comparison to our model. Now, we image this to try to get a depth measurement, which we can then, again, use as a comparison to this model.
So the model itself uses tensile data gathered at various temperatures for A356, which is slightly different than the aluminum alloy that we use to create the real-world comparison. But at the temperatures that HIP is conducted at, usually around 400 to 500 degrees Celsius, those strengths are extremely comparable between the two alloys, so there should be no significant difference between the simulated hip sink depth. Now here's the simulation itself. It predicts a hip sink in exactly where we thought and about the same depth, 2.7 millimeters. And you can see here that difference is likely because the mesh is overlapping within the pore itself. So future steps are to integrate creep data into this model to help it make more of a better prediction for smaller pores. And we need to make a material card for titanium itself because we couldn't cast it here on campus as it requires a vacuum induction melting system, which was currently under service when we started our project. So here are our references.